So I'm just going to remind you of what we saw this morning, and then I'll hand this over to Direct. So I've only labeled the sort of the highest dimensional pieces in the stratification. So each of these is some sort of complex K modules. And the key things are you have some frontal Legendrian knots, and so I don't have to label all of these sort of lower pieces in the stratifications because they're all isomorphic to something else that I've written in the picture, because remember, down arrows are isomorphisms. So here is a picture of around a left cusp, and so the point is that this map composed of that needs to be the identity, and similarly on the other side. And then at a crossing we have 4 things labeled, and the cone on this, so that this entire thing right here needs to be acyclic. Okay.
So I want to make one calculation and then discuss one piece of philosophy. The calculation is the trefoil.
You have to yell more though.
Yes. I will calculate the trefoil. There you go. Here's the trefoil. And you know what you're supposed to do? You write 0 here, 0 here. And when you cross once, you're supposed to find some one-dimensional vector space. So I'll just write K to my one-dimensional vector space. And I cross again, I'm supposed to find again a one-dimensional, one more dimensional vector.
Sorry, maybe I'm stupid, but why one-dimensional and not any random given complex?
Let us put a Maslov potential.
Okay.
There's no choice for not. 0, 1, 0, 1. Okay. So that says that the cone of this morphism, whatever it is, should be a one-dimensional vector space in degree 0. Okay. And saying the cone from 0 to something is a one-dimensional vector space in degree 0 means that guy is a one-dimensional vector space. And similarly, saying that the cone from a one-dimensional vector space in degree 0 to something is a one-dimensional vector space in degree 0 is to say that something is a two-dimensional vector space in degree 0. Maybe it's worth writing down. Okay. 2, question mark. 2, okay. 2, 1. That's the right thing. This map, no, this goes to 0 because I should put the one-dimensional vector space in degree 0 here. What am I saying? Let me use color. Okay. So I'm trying to figure out, if I was trying to figure out what should go here, the condition was that there is an exact triangle between whatever went here, this mystery item, and the one-dimensional vector space in degree 0. Why one-dimensional? Because we're discussing rank 1, means sign at the beginning. Why in degree 0? Because this had Maslov potentials. That was the rule for deciding what should go. So saying that this is a one-dimensional vector space in degree 0 means I write K here, and in the long exact sequence I also have a 0. And saying this is a one-dimensional vector space in degree 0 means I write K here, and in the long exact sequence I have 0. There's only one way to fill this up to make an exact sequence. Is it okay? working over something more complicated in fields, then there might be more than one option. Yeah, I mean, if there was some non-trivial extension of this by this, then it could be another option.
So the Maslov measures the rank. The Maslov measures the rank.
Maslov measures the shift. Let's look here.
Okay.
Okay, so for this one, let's study this one. So in this one, and maybe I'll again use color. I'll color this one now. So then I'm supposed to have K2. Okay. So of course, this map is maybe it's not. And what's supposed to happen? Since this is degree 1 Maslov potential, that's telling me the cone is K shifted back by 1. And this one being K2, K squared means that. Okay. I mean, the cone is supposed to be the thing that's K in degree -1. There's a 1 Maslov potential. And so that tells me I should write 0 here. And I knew that this K was this K, so I knew already that it was 0. And so I could learn also in that way that should be this. So maybe so I'll review. The cone over this morphism is supposed to be 1-dimensional in degree given by minus the Maslov. That's the rule by which we make these things. Of course, this rule is deduced by saying, I want a sheaf microsupported in this knot. And then there's like, sort of short or long calculation letting you extract this rule. Then you extract this rule. Okay, so now the data of this sheaf, as maybe you learned this morning, is prescribed to you by this kind of stuff. And let's just see what is being said at these various regions. So at this crossing here, I'm supposed to know that 0 to k plus k to k squared. Yeah, the total complex of this is acyclic. Right? That was the condition. And what does it mean that the total complex is acyclic? Well, it means this map is an isomorphism. And what does that mean? That just means the image of this map is not the same as the image of this map. Right? So, like, the condition is at each crossing, so also this one, this map and this map have different images. This map have different. This map and this map have different images. Let's see one more thing. So what happens at this crossing? Maybe I pause. Does that make sense to everyone? I see at least one frown. Turning into a smile might be too late. Okay, so how about this question? It's supposed to be that if I compose this map with this map, I get an isomorphism. What does that mean? That means the kernel of this map is not the image of this map. As long as that's true, that composition is an isomorphism. So now let me specialize to Z mod 2 so I can actually enumerate things. Maybe even before doing that. So like, I will choose coordinates such that this map is the inclusion of the 1, 0 basis vector. this map is like
Har ni hört här nu det senaste? Lyssna på det.
1, 0. I can choose those coordinates. I can choose coordinates that this map is the inclusion of the 0, 1 basis vector. And then the question is like, well, what happens to, so what other maps do I have to discuss? I should look at this map, and this map. So let me just go over here. This map is a 0 basis vector, this map is a 0, 1 basis vector, then I have this map, and this map. And now for this, let's just work over Zmod 2, so you can just list things. And the image of this map should not be the same as the image of this map. I mean, by the way, when I said I could choose this one to be the 0, 1 basis vector, why? Because its image is something that is not this one. And at this point, I'm still free to fix the base, still free to change it. But once I've fixed both of these, I've completely fixed the basis of this thing. So I've used up all the flexibility. So now the image should not be this, so it could either be this one or this one. And in this case, well, the image should not be this, so it could either be this one or this one. And in this case, it could either be this one or this one. And how about this last map? Well, for this last map, the thing that's important is its kernel. So let's discuss what its kernel could be. And there's, so in this last column, I'm going to somehow write what the kernel of this map might be. And it can't be the same as this. So maybe the kernel is 1, 0, maybe it's 0, 1, here maybe it's 1, 1, maybe it's 1, 0, here maybe it's 1, 1, or 0, 1, and here maybe it's 1, 1, or 1, 0. But it's also not supposed to be the same as this. So I should cross out whichever ones turned out to be the same. I have now produced for you all the Zmod 2 sheaves on this picture. You may observe that there are 5, and you may know that there are 5 augmentations over Zmod 2 of the truffle. So this is the historically the first reason we believe this thing.
Can I add something? So there's a nice way to generalize this to other fields besides Zmod 2, and in such a way so that you actually see that this set of such things. So this is essentially what you need is 5 vectors in k squared that are so that they're arranged in a circle so that any 2 consecutive ones are not proportional. And there's a nice way to see that this set is actually a variety, and the variety is given by in coordinates by the vanishing locus of something that looks like 1 plus a plus c plus abc, which is something that you may recognize from the DGA of the trefoil. Maybe I won't actually do that, but hand it back to you.
I'm certainly not going to do that.
I learned how to do it, so
You can do it if you want.
do your thing first.
Wait, can I ask you a question first?
Yes, please.
So, Noemi in her talk, were you at Noemi's talk?
I was forbidden from coming.
I see, okay. So, I mean, she has this tabulation of the augmentations over Z2 where she said you can send B1, B2,
Oh,
B3.
good. So you all know that there are 5 of these.
Yeah,
Oh, fantastic. Yeah, good.
yeah. Can you see the 5 augmentations from your tabulation? Can you deduce?
You want to know which one is which one?
Yeah.
Okay, so I'm going to do the thing that I said I wasn't going to do. Because I think it'll become sort of clear from there. So we have I've identified this with its kernel instead, so that becomes this last map from k into k squared. It's just mapping the generator of k into whatever the generator of the kernel is up there. So now I have, so this is what I was saying, that I have now 5 This gives me 5 elements inside of k squared so that they are pairwise, at least adjacent ones are pairwise distinct. So that is this, by the way, the variety of such things, this has a name, I just don't remember what it is.
A2 cluster.
I thought it was named after a person. Yeah?
But it may have some more specific.
Okay.
What was the name of the vector?
A2 cluster variety. Okay, so as Vivek said, we can assume that we can assume that this map is given by 1, 0, and this map is given by 0, 1. That is to say that the unit gets mapped to 1, 0 in here, and this one gets mapped to 0, 1. And then the clever thing to notice, which was pointed out to me, so this was not my observation, is that what does it mean? So these two now generate k squared. So what does it mean that the next one maps to something that is different, that's not in the span of this? What it means is that it maps to something that looks like this plus some multiple of that. Right, so this one gets mapped to, too many arrows, sorry, to 1, 0 plus some multiple of 0, 1. Or maybe another way to say this is that this maps to a line inside of k squared, and there's a unique point in that line that is of this form. This is just because these two things actually generate k squared, and it can't be proportional to this. Okay. Then you just keep doing this. So the next one, now there will be a unique element inside of the line that's the image of this map that looks like this plus something times that.
Yeah.
All right, so 0, 1. I'm going to give these things names. So this is V1 and this is V2. So we go V1, V2. The next one looks like V1 plus A times V2, where A is in K. The next one is V2 plus B times V1 plus A V2. And the last one is V1 plus AV2 plus C times V2 plus VV1 plus AV2. So in each case, I'm taking the one that's 2 before it and adding in some multiple of the one that's right before it. Okay, and what is this? How did I do? So this is V1, 1 plus CV times V1 plus A plus C plus ABC times V2. I have no idea if this is correct. Did somebody check my algebra and see if this is right? Oh, actually, this is pretty good. Yeah. So this is the 5th one, right? And what does it mean that? So this one is also supposed to have a different image than that one. So what that means is that this cannot be the same as this cannot generate the same line in K2 as this one, which just means that this is non-zero. True? So what we get is we get the set of A, B, and C so that A plus C plus ABC is non-zero. Okay, so this is not quite what I promised you, but the point is that you can, whatever this is, if it's non-zero, you can rescale these things so this is actually equal to 1 or minus 1 or whatever you want. The point being that you can multiply A by lambda A, where lambda is the inverse of whatever this thing is, and B is multiplied by lambda, replaced by this, and C is replaced by that. Right, and then so lambda, I think, is A plus C plus A plus C. Okay, and then if you replace them in this way, then you get that exactly that A plus C plus ABC equal to 1.
So the last one's adjacent to the first one, like it's.
That's correct. Yeah, this last
so that's
one.
why you get that. Okay.
Yeah, it's now gone. But this last one was a little bit weird because we were looking at kernels instead of the images. But that's correct. Yeah.
Okay.
So you have these 5 things arranged in a circle, and any 2 adjacent ones cannot be the same. And so up to sign, this is what you remember from the differential of the trefoil. And this actually works for any 2n Legendrian 2n torus knot. It's sort of a nice computation. Okay, you can come back there. Did that? Why did I start talking about this? Here, Marco, you asked a question. Somebody
Yeah,
asked.
I asked if you could recover where B1, B2, and B3 are sent.
Yeah, so now you can just reverse this process and say for the 5 augmentations that satisfy this, then go backwards and you can figure out what the 5 things were. I don't know which one is which, but it's on these guys. Okay.
I wanted to say something about this augmentations or sheaves business, or like why we at all begin thinking about sheaves in this context.
Wait, before you start, can I ask a question about the trefoil computation? Like, why, how did we know that, like, you know, we just wrote, like, K and K2 is like K squared. Is there, is there, like, a reason why we knew that maybe there was some sort of weird thing where things ended up being, like, quasi-isomorphisms from the derived category or something like that, where...
Actually, that's kind of long.
Okay, alright.
Yes, but a priori, you should avoid about that. So, okay, I'll tell you the answer. The answer is that because the Maslov potential was only in degrees 0 and 1, you can argue, as I sort of did in certain cases, that the sheaf is at the cohomology of the whatever complex of sheaves you have is concentrated in degree 0. But you saw some sort of instances of that argument. Once you know that, you can show that in fact you can represent the thing by just vector spaces at each point. Okay. So let's draw this picture again. One, two, three. So let me explain how you might produce a sheaf given an augmentation. So let's say you have this knot and you have an augmentation of it. And like, what is a sheaf? Sheaf is supposed to be a piece of like some sort of vector space or complex or whatever at each point. So let me tell you what will be the sheaf at this point. So to do that, I introduce some sort of fictitious guy. And this guy, he's an unknot, and he has some canonical augmentation. Unknot has one canonical augmentation. Okay? And now I compute the bilinearized homology from this, I forget which direction it goes, but there's some kind of bilinearized homology which is generated by this ray point. And that is the one-dimensional vector space that I put here. Now, okay, what do I put here? I take like another sort of test person. And this time, there are 2 ray points. And so again, I put the bilinearized homology. And if I did what I did in some sort of correct way, then between this one and this one, there's a ray point. And I can use that ray point to get a map between these. So I can use, actually I forget which ray point it is, but I use some ray point between this red one and this other red one to give myself a map. And composition with this ray point. And this is how you produce, like from an augmentation on this black thing, by using some, like large collection of these fictitious red ones, you produce a sheaf. That's what? Oh, yes. What Lenny was not saying out loud is the original name of this is the front-licking functor. That's all I had to say.
Why were you thinking about these fictitious I'm not. How did they come about?
You can imagine them.
Yeah, sure. Well, I can. Now I
Like,
can,
this,
but
I mean, this is like this both idea is that this is actually the fluoromology with the fiber, but the fiber is not so nice to draw, so maybe we draw it like this kind of very curved unlock instead.
I mean, maybe say it a little differently. If you know about Nadler-Zaslow correspondence, that's some sort of associate. If you have somehow Lagrangian and cotangent bundle, you're supposed to produce a sheaf on the base, and you produce it by taking. When you want to know the stalk at a point, you take Hom in the Fukaya category with cotangent fiber,
So that's family flow cohomology.
and that gives you a map from Fukaya to sheaves. There's some always the most difficult part. So the map, and you can always produce a map in this way. Although like if you read this NRSSZ paper, augmentations of sheaves, you will not find this picture. Because in any case, the most difficult part of the story is not producing the map, it's always checking that it's surjective. What?
Well,
Surjective, yeah. Checking that it's surjective. And this sort of picture doesn't help you at all with that.
Is there a place where you can find this picture?
I think I put it in my blog at some point.
Okay.
But no.
This is the secret blog that is not actually secret. Okay, well, the speaker has disappeared, so. Are there any other questions for Vivek? Okay. Well, I think probably then you're free. Please bring back in chairs if you brought.
we should thank Vivek at least.
Oh yeah, thank Vivek.